So this is our first webinar series for this year. Today we will have talk from Mr. Danny Haryanto from University Science Malaysia. Alright, his topic today will be the introduction to model development with Phyton. I think Mr. Danny will introduce himself about his background. And for the reminder, please mute your mic during the session. For those who like to ask, you can raise hand or unmute your mic during the session if you have a burning question. So if you have a question but you don't want to ask during the session, please put in the chat room so that we can collect the question. Then we will have a Q&A after end of the talk. All right. So reminder, please unmute your mic. And then I think at end of the session, we will have a group photo. Just open your, if possible, open your webcam so that we can have a group session. And for those who we request that all of you register the attendance so that we can have record. And if you like to join the society, we will email the registration form according to the registered email for today. Yeah. Okay. Without further ado, I would like to invite Mr. Danny to give his talk. Okay, Danny.
Okay.
You.
Thank you, Mr. Fauzi. First of all, I would like to thank the organizer for organizing this webinar. And also, I would like to thank everyone that have spared some time to join this webinar. Let me see if I can share my screen. Okay. So today I'm going to give a little bit of introduction to model development with Python. So for those of you who are familiar with Python, this will be quite straightforward, quite like a simple introductory course. But for those of you who never used Python before, I'll try my best to explain step by step on how you could develop a model with Python. So let's begin. So what we are covering today, first of all, we'll go through the brief introduction on machine learning, what it is, and how many types that we have, how many types of machine learning there are. And then after that, we'll go through a little bit of an introduction to Python. Why do we use Python for machine learning? And then at the end, we'll have a live coding session with me. I'll go through how we could develop a model with Python, a live coding session. So you could have a look on how we could do it with Python. So first of all, what is machine learning? Well, Arthur Samuel defined machine learning as a field of study that gives computer the ability to learn without being explicitly programmed. So he defined this in 1959. And what it means essentially is that traditional program, when you program it, it's hard-coded. You have a certain set of rules and that's it, right? You cannot go, if you introduce a new instance that is not within the set of rules that you've set, then the program might not be able to process that information. But with machine learning, the more data that you fit into the model, the more data that you fit into the algorithms, they will be able to generalize with more and more input, more and more data in the future. Tom Mitchell gave a more recent definition. He says that a computer program is said to learn from experience E with respect to some task T and some performance measure P. So what he's trying to say is that a computer program is said to learn if you feed it with some data. So experience here is data, right? And then some task T. So task is what are you trying to get the model to predict? So for example, if you want to predict the quality of the water, or do you want to predict the air quality, then the performance P is the performance measure that you use. For example, RMSE, root mean square errors, or you use R square normally to measure the performance of your model. So if the more data that you introduce to the model, it should perform better. In theory, it should perform better. So it says that the performance on T as measured by P should improve with experience E. right? So those are the definition of machine learning from two of the most popular scientists in this field. Next, let's take a look at how many types of machine learning out there. So we could classify it into three different types, right? First of all, does it need human supervision? So here we could separate it into supervised learning, unsupervised learning, or reinforcement learning. So these are a pretty interesting concept that we're going to discuss more about later. Secondly, we could ask ourselves, does it able to learn incrementally? Which means that can we feed data online? You know, keep feeding it data and then it gets better and better. If it couldn't, what does it mean, right? So we'll take a look at that as well. And how does it generalize, right? If we train a model, we want to know how could it generalize with new information that we fit into the model, with new data, right? Does it generalize by referring back to the previous training data, or does it build a model? So we'll take a look at that as well. So first, supervised learning. So what is a supervised learning? Supervised learning essentially is you supply the data with the proper labels or the proper solution to the machine learning model, right? So what it means is that if you give the model a set of data, you label each and every single one of the parameters and columns, and you tell them which is the solution. So to give you an example, let's say you want to predict air quality. So you supply this information such as meteorological data, temperature, humidity, wind, and speed, wind speed and wind direction, right? And then you tell the model if these are the conditions, what you should expect in terms of air quality, right? So that is how you train the model. Once you train the model, and then you introduce a new set of data, that's what we call testing. You want to test the model. Does it work based on the training that I've done? So when you test the model, you introduce just the input data, right? It should be able to predict the air quality based on what it learned from the training data. Another example, for example, it could also process image file. So for example, if you take a picture of a plant here, it could tell you what kind of plant it is. But before it could predict what kind of plant it is, you need to train the model. So when you train the model, you maybe have thousands of pictures of plants and you label them one by one, right? You need to tell them if this is a picture, what plant is it? If there's a cactus, then you have to tell it it's a cactus and this is how a cactus should look like, right? And then once you develop the model, you should be able to use it to predict in the future, to predict what plant it is just based on the picture. So you can take a picture and can tell you what plant it is. Another example is, you see, if you zoom in into the leaf, you can even tell if this is a healthy leaf or an unhealthy plant. Does it need water, or, you know, if it's unhealthy, what does it need? More nutrients or something else, right? So based on the model that you train, you can actually predict this kind of thing. All you need to do is to supply information, to supply data into your model. So if you want to do this kind of prediction, you need to supply thousands and thousands of pictures of plants' leaf, their structure. How does it look like if it's healthy? And how does it look like if it's unhealthy? And you have to tell the model, you have to label them. This is how it looks like if it's healthy, and this is how it looks like if it's unhealthy. So once you develop the model, you can use the model to test more data by just introducing just the picture itself without telling it anything, and you could predict if it's unhealthy or healthy based on the training that you have done on the model. Now, even as you can see here, we have a dash cam video. Machine learning model could also process such file type, such video, and it can tell you which one is the car, for example, here. So this is what we call object tracking. So as you can see, it could detect all the cars there is in the picture. So when you train the model, you introduce a lot of this video footage of web dash cam, of car dash cam, and you manually label them, which one is the car. And then when you train the model with thousands and thousands of this footage, by the end of the day, you should expect the model to be able to detect by itself if you introduce a new set of videos without labeling them. So they should be able to detect which one is the car. So this is what we call object tracking. Now that's supervised learning, right? So let's take a look at unsupervised learning. So in unsupervised learning, essentially it's just giving a bunch of data to the model without labeling them. So without telling the model anything. So it's like, here is a bunch of data and go figure it out, right? So for example, here you could see, this is an example of clustering. right? So you supply a bunch of pictures. There are cats and there are ducks, right? But you didn't tell the model which one is which. So you just give them a picture and that's it. You didn't tell them which one is cat, which one is a duck. So with supervised learning, you need to tell them. But with unsupervised learning, you don't tell them which one is which. And then it goes through the clustering algorithms, and then it will cluster the pictures together based on the similarity index, based on the group they think belong to the same cluster. So in this case, you can see that they clustered the ducks together and they clustered the picture of the cats together, but without knowing that those are cats and those are ducks, right? Another example is anomaly detection. So with anomaly detection, let's say you have a bunch of data and then you train the model with that data, they get a sense of what the normal type of data is, right? What the normal operating condition is. So when you introduce a new instance and it is way out of the normal condition of the data, it will detect it as an anomaly. So where can we use this? For example, if you are in a plant, in a chemical plant, and then there are a lot of processes going on. So if one of the process ran off the normal operating condition, and then it will inform you that there is an anomaly, right? So it's very useful for fault detection. So that is unsupervised learning. You didn't give any labels on your data. You just give him a bunch of data, and then the machine learning algorithms will figure the solution out by themselves. What about reinforcement learning? So this is a newer, sort of like not as popular as unsupervised and supervised learning, but this is quite an interesting concept. So with reinforcement learning, you have a learning system called an agent, right? So the agent will observe the environment and perform certain action. When they perform the right action, they will get rewarded with some kind of points. But if they didn't perform what they are supposed to perform, if they did something wrong, they will get penalty, right? They would get penalty. And they will keep repeating this process until they keep getting things right and they minimize the mistake that they made. So an example of this is like, if you have seen those Boston Dynamic robots, the robots that could walk like human and some can walk like animals, those robots actually use this concept to learn how to walk. So if they fall, they will have a penalty, sort of like a penalty and negative points. But if they did it right, they will get a positive point. So that is reinforcement learning. Okay, so now what about batch versus online learning, right? So how does the model learn? Does it learn incrementally, or do we need to give a bunch of the data to the model at once and train the model and then deploy it? So batch learning is a type of learning in which you need to supply the whole data set to the model and then train the model with those data set. And then if the performance meet whatever you have targeted for example, at least 80% accuracy, then you can deploy that model, right? So this model cannot learn incrementally, which means that if you have new data later on in the future, you cannot just feed in the model and then it will update itself. So it doesn't work that way. So if you have a new data in the future, you actually have to retrain the model from scratch, from beginning again, from scratch, and then make sure that it meets your performance, and then replace the old system with a newer system. By doing it this way, it actually takes a lot of time, right, to train the model, and it takes a lot of computing power. But then there are some process that doesn't require you to keep updating the model. Then this batch learning system works very well with that kind of process. However, if you have a process that's very dynamic and requires changes rapidly, then you will need a type of learning called online learning. So online learning means that your model will be able to learn incrementally. So once you train the model with certain data set, it could be a very small set of data set, and then you deploy it, you can keep feeding more data into the model, and the model will update itself and get better and better depending on the quality of the data that you introduce to the model, right? So by doing so, you don't actually need that much of training time. You have reduced your training time significantly. And also, you don't require that much of computing power, right? Because now you're just slowly feeding in information, data into the model, and the model just slowly updates itself. The problem with online learning is that when the quality of your data that you feed into the model is bad, let's say in a certain time you have a bad batch of data and you feed it into the model performance will get worse and worse. So it really heavily depends on the quality of data that you introduce to the model. But if you have a process that is dynamic and require changes rapidly, just make sure that you have a good set of quality of data, and then you can use this online learning system. Now, what is the difference between instance-based versus model-based learning? So this is how they generalize, right? So instance-based model, the way they generalize is based on comparison through similarity measure to the previous data that we have introduced to it during training, right? So it doesn't develop any model. It just compare them to the previous training examples and try to make prediction from those data set that we gave to the algorithms, right? So in a way, if you introduce a huge data set to the model, you cannot remove that model anymore because they require it to compare to the new input that you might introduce to your model. So it's not very good, but there are certain scenario in which you need to use instance-based learning. One example is KNN model, right? K nearest neighbor. So they use this instance-based learning concept. Another one is called model-based learning. So this is the more popular version of the learning compared to instant-based learning. So in model-based learning, you introduce a bunch of data, and then they will actually develop a model based on the data that you introduce to the algorithms. So once they build the model, they no longer require the original data set that you introduced to the algorithm. So they will discard, you can discard the data set safely, and you will still have the model that could predict whatever output you set it out to predict. So model-based learning is the more preferred version compared to instance-based learning. Okay, so you get an idea of, a little bit of an idea of what machine learning is and how many types that we have. Now let's talk about Python, right? Why use Python? There are many programming languages out there that could do data analysis and machine learning as well, such as R, even MATLAB. You could use MATLAB as well, but why Python? Now, the first reason is Python is completely free. Python is completely free, so it's accessible to everyone. Matter of fact, I think most computer today has Python built in by default, right? If it's not built in by default, you can just easily download it from their website, and it's completely free. The second thing is Python is open source, which means that everybody could build libraries and frameworks and share it out. So Python has a lot of libraries that you can use. A lot of libraries that you can use, a lot of functions that you can use, and all of them are completely free. The third reason why is Python is a very easy language to learn, right? Python is heavily based on English language. So even though you have no programming background, if you look at a Python code, you should be able to easily understand what it means or what it is trying to do compared to other programming language. The fourth reason is Python is simple and the syntax is very compact. What it means, if you compare this to other programming language, for example, to perform a certain function, you will need at least 10 lines of codes. But with Python, you probably could do the same function with only 1 line of code. So Python is very simple. It's very simple and compact. And the fifth reason, one of the most important reasons, is Python run on every major operating system. So you can run it from Windows, or if you have a Mac, or even if you have a Linux, you can run Python. How do you run Python, right? So the first and maybe the most accessible way is to use terminal. So if you already have Python installed in your computer, you can just open up terminal, or if you're in Windows, you can use CMD, a command line tools, and you can just run Python from it. I don't prefer this because it can get quite complicated if you're not familiar with how the terminal command line tools, the syntax works. So I prefer the second option. It's called integrated development environments, right? So it's sort of like a software that allow you to write Python code and import files, import libraries easily without having to write the long terminal line codes. It's very simple. The third option, if you don't want to install Python, if you don't want to install any other library, you can use Google Colab. So Google Colab is sort of like a web application by Google that is hosted on Google server. So you can just open it up, sign in. You add a new notebook and you can start writing Python code and running Python code straight from the web application. So you don't have to install Python, you don't have to install any libraries, it just works, right? So Google Colab is very good if you are new to Python and just want to test it out. And it's completely free too. Okay, let's talk about Python libraries, right? So a library in a Python essentially is just a group of modules that you can use that have already been developed by other developer and shared that you can use to perform certain tasks. So you can just import these modules without writing the lengthy code anymore and just perform the specific task that you need to perform. And with Python, there are over 137,000 libraries out there. So you can just pick any of the libraries that you need to use for your system, and it's completely free, very simple to import, and you can immediately use those modules. All right, so each library, they have thousands of modules, and each module, they have a lot of function that you could do. So you can imagine how much thing that you could do with all the libraries that Python has. So down there, these are a few examples of the most popular Python libraries. You have NumPy for mathematical equation and data frame processing. Pandas, also for data frame processing. Scikit-learn. So Scikit-learn has a huge machine learning modules that you can use. They have a lot of models ranging from regression, classification, or even a neural network model. So Scikit-learn is a very good library. You have OpenCV. OpenCV is for object tracking, so of like image recognition or object tracking in a video. A little fun fact, Tesla, when they first began developing their autopilot system, they actually use OpenCV in certain part of their autopilot system. So it's a very powerful library. And then we have TensorFlow. TensorFlow is a library from Google that allow you to do mostly neural network stuff and deep learning stuff. So a really interesting library as well. And then you have Matplotlib. Matplotlib allow you to plot a different type of graph to visualize your data, right? So these are a few of the most popular library out there in Python. Okay, so how do you develop a prediction model with Python, right? So we could actually, in a big picture, just summarize it down to 4 simple steps. The first one is you need a data set, right? So no matter how you obtain your data set, you can probably download it from a website. You could scrape the web. You can obtain maybe your data set from a lab or something. Or if you want a free data sets that you can download easily, you can go to Kaggle. So Kaggle has a lot of free data set there. I think about 50,000 data sets that you can download from. So it's completely free. You can download it and test it out yourself. And then after you got your data, you can start importing all the necessary libraries, right? All the necessary dependencies that you may need for your model. Once you have done that, you can proceed to cleaning your data, because data most of the time they need cleaning, right? They have missing values. They have a lot of variables that you may not need. So you need to clean those data and then pre-process them. Pre-process them essentially like perform scaling, perform transformation, perform data reduction. So that falls under pre-processing. And then lastly, once you have pre-processed and then you have a clean data, you ensure that your data is a really good quality data. You then can introduce it to your model, right? You can start training your model using those data and then get maybe a really good performance on the training set. And then after that, if you get a good performance on the training set, you can proceed to test your prediction model with unseen data, with the data that the model have never seen before, and see if it still perform as well. Normally it won't perform as well, but if you have a good performance, it will still be a good performance. So those are how you could develop a model with Python. And now let's go into the live demo, right? So for the live demo, these are a couple of information before we begin. The live demo will use a data set from China air quality, so it's from Beijing. The air quality data set is hourly measured from 2010 to 2014. So it's a lot of data, right? It's measured hourly, it's a lot of data. The input to our model will be meteorological data. And the output that we are trying to predict is PM 2.5. So PM 2.5 is a type of air quality that's actually one of the most dangerous pollutants out there. So it's a type of measure for air quality called PM 2.5, right? So we'll use meteorological data like temperature, humidity, wind direction, wind speed to predict PM 2.5. The libraries that we're going to use is NumPy, Pandas, scikit-learn, Jupyter Notebook. Jupyter Notebook, you'll see later, is for us to easily visualize the code, and we can run each line of code individually. It's really good. I'll show it to you later on. And we have Matplotlib to plot graph, and we also have Seaborn. Seaborn is also to plot graph, but a little bit more sophisticated graph. As for the model, we'll compare two different type of model. So we'll use a very simple model from scikit-learn library for this demo. We won't go into a complicated model, so we'll just use a very simple model from scikit-learn. We'll use linear regression and random forest regression. So okay, let's move on to our live demo. So if you guys want to go along and try to code along with me with this live demo, you can do that too. Just go to Google Colab and sign in and create a new notebook, and then you can start writing codes. Maybe follow through with what I'm trying to do here. Okay, so the first thing that you need to do is to import the required libraries. So this is one of my favorite things to do at first, is to import the required libraries, right? So later on, when you start processing your data, you don't have to import it anymore. But you can still do that later on, but it's just convenient if you import everything at first. So the libraries that we use is, see here we import Matplotlib, SPLT. So what this means is we import this whole library and we call it SPLT, so that later on when you want to call this library, you don't have to type the whole thing. You just have to type PLT and you are calling this library out. So it's a convenient way to simplify your code. So you import pandas as PD and NumPy as NP. And the same for Seaborn. Import time in order to measure the time it takes to, let's say, train a model. We have max. This is for us to later on calculate the root mean square error of our model. And then you have, from scikit-learn library, we're going to import some pre-processing tools in order to scale our data later on. And then also to split our data into training set and test set. And then we also, from the model modules, we're going to import linear regression model. So importing is very straightforward. You just have to type in import and then the name of the library or modules that you're trying to import. So very straightforward. Once you have import your libraries, the next thing you can do now is to load and overview the data, right? So you want to load your data set into Python. There are a couple of ways to do this, but I think this is one of the simplest way to do it. And you always want to make sure that your file is in .csv form. So .csv form is the most popular form of data format if you are going to do data analysis or perform machine learning tasks. You could use Excel too, but .csv is a more compatible file type with Python. So once you have your file, you just need to find out where the file is located in your computer. So this is the folder path of your file. So you just name or name your path name as CSV path, or you can name it as any variables. So later on, you just need to call the particular file with Panda. So here we set our data set is equal to Panda read CSV and then the CSV path. This is where your file is located, right? So what this does, what this line of code does, is to convert your CSV file into a data frame so that Python could read the file, the data. Okay, so once you have loaded the file, the first thing I want to do is to overview the data, to look at our data. What kind of data do we have, right? So the first step is to display the shape of the data. We want to know how big is this data. So from the shape, you can see that this data has 43,824 rows and 13 columns. So it is quite a big data, right? It has almost 44,000 rows. So it's quite a huge data. Once we know the shape of the data, we get a rough idea of what we need to do with this data, right? So the next thing we want to do is to display the first 100 rows of the data set. Or you can display 200, 300, 400, doesn't matter. But here I'm displaying the first 100 rows of the data. And since with Jupyter Notebook, you cannot just display the whole data set. Here, it will just show you the first 5 and the last 5, right? So as you can see from the data, you can already see all the columns that you have. You have number, year, month, day, and all these parameters. And then on the left side is actually the rows, right? So you can see each and every line is the sample, each sample from your data set. So you can see this NaN value. It means that you have a missing value in your data. So we'll see later how we could handle this such missing value, right? And then under this CBWD is combined wind direction. So under combined wind direction, you can see that the value is actually not a numerical value. It is a text or a string, right? So machine learning algorithm, they don't really like to work with text attributes. So most of the time we'll convert this into a numerical attributes. So for example, this is northwest, so maybe we convert this value into 1. So every NW or northwest will be 1, right? So we'll see how we can do that later on. Okay, so these are the parameter description. You can see what every single parameters means. So PM2.5 is the concentration, temperature, pressure, combined wind direction, cumulative wind speed, cumulated hours of snow, and cumulated hours of rain. So these are all the abbreviation for our parameters here. Okay, so once we have seen our data, we know that this number parameters is unnecessary because we already have index for our data, right? So Panda automatically index our data. So this number is unnecessary for our model. So what we do is we're gonna drop the number columns, and it's very easy to drop it. You just redefine your data set, and here you just data set, which is what our data is in. So our data is, we name it data set. All you gotta do is introduce this function called drop, and then all it does is just it drops this particular number parameter. So all you need to do is just to tell it which parameter you want to drop. So in this case, it's number. So it dropped the number columns, and if we check our data set again, the number is no longer there. So we have successfully dropped the number columns from our data set. So once we have removed that unnecessary columns, the next thing we want to do is to get more information from our data, right? Such as what's the data type and how many counts of data in each columns, in each parameters. So we can do that with dataset.info. Again, Python has a very simple script. By looking at it, you already know what it's gonna do, right? So dataset.info shows you the information of your parameters in your dataset. So for example, here you could see this is the count of the data count of each parameter that you have. So everything is actually seems okay, right? 43,824 is the same as the range index. But for PM2.5, as we have seen earlier, there are missing values. So it shows 41,757, which is less than the supposedly what we should have, which is 43,000. So we have less PM2.5 data with data points, which mean that there are missing values. Okay, so here on this side, you can see these are the data type of each of the parameters. So you have int64, which means integer. So integer is just a numerical attribute without decimal points. 64 is just 64-bit. Float is just numerical attributes with decimal value. So if it has decimal value, then you call it float, right? And down there, you can see another interesting type here called object. So why is it called object? Now, because we have seen earlier that cumulative wind direction is not in numerical attribute, but it's a text attribute. That's why I call it an object. It's not a numerical attribute. Okay, so we're gonna need to do something with this object variable because we need to convert it to numerical attributes. So once we have seen the data counts and the type of the data that we have, the next thing we want to do is to get a better understanding from our data by doing a statistical overview, right? So here what we do is we describe our data, right? So it's just dataset.describe, and then you can see the information, the statistical information of your data. So you can see how many counts that you have again, and you can see the mean value of each parameters. the standard deviation, the minimum value, the maximum value, and these are all the percentile, 25, 50th percentile, and 75 percentile. So 50 percentile essentially is just the median of your data. So you can see for every parameters, we have all this information. Okay, now that we have sort of like a brief understanding of the data that we have, and we have seen that the data is not very good, right? They have missing values, and some of the variable need to be converted to numerical attributes. So what we're going to do next is to clean the data, right? To clean the data and pre-process the data. So the first step that I like to do is to convert the categorical variable to numerical attributes, right? So what we have before, which is the cumulated wind direction, which has been listed down in a text as a text attribute, we want to convert them to numerical values. So the first thing that we do is we want to display how many different text attribute that does this parameter has, right? So what we do is we type dataset, again, this refer to your data, and then you did this square bracket to tell them which columns or which parameter that you want to see, right? And then you call this value counts function to let you know how many different text attributes that you have and how many counts of those in this particular column. So you can see that the highest counts is we have southeast and then northwest. CV stands for column and variable, which means that there are no specific direction of the wind, and you have northeast. So you can see that you have 4 different type of text attributes inside your parameters, right? So the next thing you want to do is to convert them into numerical attributes. So what we do is we do label encoding. So label encoding will convert your text attributes into numerical attributes in terms of ascending numbers. So for example, the first one will be 0, and then 1, 2, 3, 4, and goes on. Depends on how many text attributes that you have. So to call this function, all you got to do is to call this pre-processing modules from the scikit-learn library and call the label encoder, right? You can name this. I named this LE to just simplify the code, but if you want to name it, you can just put the whole thing right here, but it gets more complicated. So I have named this as LE, and then what you need to do is to designate that particular data set that you want to perform label encoding on. So that is your cumulative wind speed. So you did an open and close square brackets again. And then you just call this particular function and fit transform this parameters into numerical attributes, right? So once we have done that, we can check from the value counts again that it has now been converted into numerical attributes. So you see here, before it is NE, and now it's just 0, right? Before it's SC, and now it's just 2. So now it's a numerical attribute. It's still a categorical variables, but now it's in numerical attributes instead of text, so that your machine learning model could easily process them. Okay, so once you have seen that the categorical variable has now been converted into numerical attributes, the next thing that we could do is to handle the missing values, right? Again, you can check the data type here. You can see that it's no longer an object, but an integer, right? So it has been successfully converted to numerical attributes. So to handle the missing values, there are a couple of ways to handle the missing values. You can either remove that particular rows with missing values, but then it means that you're going to lose a lot of data. So normally I don't like to do that. What I do instead is to impute, to replace the missing values with the median of that particular data set. So for example, here, if we check on how many missing values that we have for that particular data set, we can see that PM 2.5, we have 2,067 rows of missing values, right? So for PM 2.5 itself, we have this much of missing value. The other parameters, as you can see, there are no missing value. So we only have to take care of this PM 2.5 missing values. So what we're going to do is we are going to import the library to perform this imputing or the median value substitution. So we call the scikit-learn library, again, from scikit-learn.impute, we import simple imputer, right? We import simple imputer. So this is the module that allow you to impute the missing values. Again, I like to name my modules. So I named this as imputer to keep it clean and simple. And then I fit the data set with this simple imputer modules. And then you don't have to tell it different. It's different from label encoding, right? Label encoding, you have to tell it which parameter that you want to perform it on. But for simple imputer, it's able to detect which column that has missing value, and it will just automatically replace them with the medium value of that particular parameters, right? So for example, here, I don't need to tell it that I want to substitute PM 2.5 missing value. It automatically know that PM 2.5 has missing value, and it needs to be substituted with median value, right? So here, what I did was to fit and transform the data set again. And then once I've transformed, I want to convert it back to Panda data frame, right? So if you want to work with a lot of the modules on Panda, you need to convert it back to Panda's data frame. So that's what we do. We name this new transformed data set as X here, and then we convert it back to data set and just insert that particular transformed data set here in the information required by Panda, right? Here is the X for the rows of data, and the columns is essentially the name of the columns. We want it to be the same as what the parameters is before in the dataset columns, right? So we just call dataset.columns, and it will name the transformed dataset the same way as our original dataset, right? So it won't change the name of the parameters. Okay, so once we have done this, it's normally good to re-index your dataset after you do the cleaning, because sometimes your data the organization or data could get jumbled up, so you just want to re-index your data, right? To re-index data is very simple. Just again, call that particular function .resetIndex, and then it will just re-index your data. Once you have done that, you can check again whether or not your missing value has now been imputed. So if you call the .info function, you can see that the PM 2.5 now has 43,824. So it has the complete rows of the data set, right? It no longer has missing values. And if you check on the missing values, it's now 0, right? So you now don't have any more missing values, right? So you have successfully impute your missing values with the median values of that particular parameters. Okay, now that we have a clean data, right? We have a clean data, we can further do further analysis on our data. So now if you check the statistical analysis of our data, you can see that the cumulative wind direction is now a variable, right? Before it doesn't show because it's an object variable, but now since we have converted it to numerical attribute, you can see it here. And then for PM 2.5, the mean and standard deviation slightly changed because we have already imputed the missing values, right? Another thing we could do is now we can show the distribution of the graph. So in order to show the distribution of the graph, it's very simple. You just, again, your data set, call the histogram function. Dense is just how many bars you want to have. So you can have 50, you can have 100. Color is just the color of the bar here. And the figure size is how big of a figure you want to have on display. So once you have all this, you can just show the distribution of the graph. And you can see how the data are being distributed in your data set, right? So as you can see, pressure and temperature is pretty good. IR and IS, you can see that most of the data lies on the between 0 to 5, right? So the x-axis shows you the value of your particular parameters, and then on the left side it shows you the data counts, right? So for example, pressure, right, at 1,000 psi, what's the data count? So it's approximately at 500, right? So you can see a very clear visualization of your distribution. As you can see, PM 2.5, it looks positively skewed, right, to the right. And then you can see here, these are how it is distributed. So you have mostly at between 0 to 200. So now, once you have looked at the distribution of the graph, the next thing you can do is actually take a look at the correlation, right? How is our input variables correlated to our output variables? So in this case, our output variable is PM 2.5. That's what we're trying to predict, right? So ideally, you would like your input parameters to have high correlation with your output parameters. Normally, it will give you a better prediction if you have a higher correlation. So here, to call this function is very simple. Again, you just call the core module, the core function, and then just, again, a square bracket to tell Python which is your output parameters, what's the parameters that you're trying to predict. So in this case, it's PM 2.5, and then we want to sort the value from high to low. So we set ascending false, right? So ascending false just means that it will be sorted descending order. So now you can see PM 2.5 is our output variable, and you can see these are the correlation value between, for example, wind direction and PM 2.5, or dew point and PM 2.5. So the higher the number here means that it has a better correlation with the output, right? So the more important this parameter is. So there are also negative correlation, right? So negative correlation, again, we look at the magnitude, we don't look at the signs. So even though this is negative correlation, but the magnitude, you have quite a big magnitude here at 0.23. So it does have quite a strong correlation with our PM 2.5, which means that this is also an important parameters. So in this demo, we are not going to remove any parameters, but if you want to remove any parameters, you can probably remove these parameters that has a very small correlation compared to your output variables, right? But in our demo, we're not going to remove any parameters. Okay, so you can show the Pearson correlation to get an idea of the relationship between your input and output. Another thing you could do is a heat map correlation. So a heat map correlation, we use the library from SNS, right? So all you need to do is plot a figure and tell it the figure size. This is a figure size and how big of this display you want. And then it's called the heat map function. Again, input your data set and correlation. And then you get your correlation of each variables between each variable for all of your parameters displayed, right? So you can see not just the correlation between your output and input, but also between your input variables, right? Whether or not they're also correlated to each another. So that is heat map, and it's also color coded, so you can easily see the visualization here. So that's heat map. Now we have done cleaning. We have seen how the clean data look like. It looks pretty good. It doesn't have any missing value anymore, and we have converted the object variable to numerical attributes. So the next thing we could do is to start pre-processing our data, right? So the first thing that you want to do is to split your data set into training set and test set, right? So what you first need to do is in order to split it to training set and test set, you need to tell them which one is your input and which one is your output. So our input, which is PM 2.5, we label it as Y. So in order to just extract the PM 2.5 data and drop the others data, you just have to call dataset and choose that particular variables, right? So PM 2.5. For X, we want everything else except for PM 2.5, right? So we want everything else beside PM 2.5. So what we do is we did dataset, and then we just drop PM 2.5. So we have everything else beside PM 2.5 as our X input variables. Again, we can check our input variable X if it's now, it shouldn't have PM 2.5 anymore. And if you check, again, it's true. PM 2.5 is no longer in the columns, in the parameter list, right? So once you have split them into X and Y, you can now split the data set into test set and training set. So what is test set and training set? Training set means that is the group of data that you will use to train your model, right? You will use to train your model. Test set, on the other hand, is a group of data that you will use to validate your model later on. So your model will not see your validation test set until you have make sure that you want to deploy the model. You have a really good model, you make sure you want to deploy it, and then later on you test it on your test set group of data, right? So again, 80% training set you use to train your model, and 20% test set unseen from your model. So in order to split this to training and test, it's very simple. You just need to call your scikit-learn library again. and choose this model selection module, and then import the train test split function. So all this does is to convert your X and Y data that you've split before into training set and test set, right? So here we set the test set size at 20. And as you can see, if you check the training data set, if you print it out, the X train and X test, you can see that now it's a much more data compared to before. It's 43,000. So 80% of it is 35,059 for your training set, and your test set is just 8,765. So this is also randomly split, which means that it's split it without any kind of a specific organization. It just split it randomly, right? It just split it randomly. Okay, so once you have split the data into training set and test set, you can start performing pre-processing of your data with the scikit-learn library as well. So now we do feature scaling. So why don't we do feature scaling before we split the data? So if you perform feature scaling before you split the data, you might risk leaking your data into your model, leaking your test data into your model. So your model will be overly optimistic, but then in reality, it doesn't perform as good, but because you leak the data, it becomes overly optimistic. So you don't want that. So that's why we split the data first, and then we feature scale, we scale the data individually. All right. So first, let me explain what feature scaling is, right? So in order to explain that, I'll go back to the distribution. Okay, as you can see from the value down there, that's how far, how much our data is distributed. You can see that it is at a very different scale. For example, pressure, it goes up to the thousands, right? And then for example, PM 2.5, right? It's on hundreds, and then if you go to temperature, right? It's 10, it's on the 10th, right? So they are at a very different scales. And the problem with machine learning models, it will tend to give more weight or sort of like more attention in the sense of to those parameters with larger scales, right? So in the end of the day, your model will be biased towards parameters with larger scale. So you don't want to do that. That's why you need to scale your data to make sure that they are between similar scales, right? So what we do here is we use a scaler called min-max scaling. So what min-max scaling does is it scales your data from whatever scales that you had before into between 0 and 1, right? To between 0 and 1. So now all your parameters should fall between the value of 0 and 1, right? So in order to perform scaling in Python, it's very simple. Again, from scikit-learn library, you import the pre-processing modules, and then you name the scaler. Again, I like to name my modules to simplify the code. And then you call this particular min-max scaler. So they have a lot of different type of scaling. So you can test it out actually one by one by checking out their libraries. But I use min-max scaler here because it performed the best for my particular data set. And then once you choose that min-max scaler, all you need to do is now to scale the data. So what we do is we fit and transform our training set, and then we perform transformation on our test set individually, right? So they are not in a group, they are being scaled individually. Okay, so now, once we have scaled the data, we can check our distribution graph to make sure that it has been scaled. So as you can see now, the scale is now all between 0 and 1, right? So all of it has been converted to a scale of between 0 and 1, has been transformed, right? So once we have scaled the data, we can start training our model, right? We can start training our model. Before we train the model, let's import the model that we need, right? So we need linear regression and we need random forest regressor. Again, to import the model the same way, you just go from scikit-learn library, import that particular module. So linear regression and random forest regressor. And then we also import this mean squared error metrics in order for later on we want to measure the RMSZ, which is root mean square error. So the RMSZ value to measure the performance, right? So we use root mean square error and also R square values, right? So we import this particular module as well. Once we have done that, again, I like to label my module. To simplify the code, I call this model 1 for linear regression and model 2 for random forest regressor. So for linear regression, I just keep it simple. I didn't change any of the tuning parameters. I just keep it simple. They have the default parameters. As for random forest regressor, which is a variation of decision tree model, I actually set the n estimators, which is the number of trees to 100, right? So if you set this, you can change this value. If you set it at a higher number, let's say 1,000, maybe you will get a better performance, but then it will take a lot of time to train the model, right? If you set it too low, for example, at 10, it will be very fast, but then you might not get as good of a performance, right? So here I set it at 100, just a really nice in-between value. And minimum sample split is just, so for decision tree, for random forest regressor, you need to find a minimum splitting point, right? So here I set it as 2. So the minimum sample splitting point, I set it at 2. So that is the tuning parameters that I did for my random forest regressor. So still very simple, because this model we just import from scikit-learn library. Now we go into the training. So once we define our model, we can start training our model, right? So for linear regression, the first thing that you need to do is to fit your model with the training data. So just now, we have split our data into training and test data set. So here we just input our input parameters to the model, which is the X train, and the Y train, which is the label, the output parameters. So we just give this information to our model and let it train the model. So once we train the model, we can actually check the score of the training set of data. So before we go into testing, we can check the performance of our training set. So here, what we did was, I named this MLR score. So what we did was we just we pick the model, which is model 1, linear regression, and then you call the score function, input your training data, which is X train and Y train, and then you should be able to see your R-square value. So in this case, 0.25, around 0.26. So not good, not very good. And then again, for RMSE, what we did was we called the mean squared error function. And then we put our Y train, which is the labels. And then this is the prediction, right? The prediction. So the model predict X train is the predicted Y value, the predicted PM 2.5. So it's gonna calculate the mean squared errors, and then we squared it to find the root mean square error. As you can see, it's also very high, right, at 77.5. So it does not perform as well. So if you check the test performance by just changing the data into your X test and Y test, which is your testing data set, you should be able to get your performance of your test data set. And again, the performance is not good, right? So if your training is not good, obviously your test set is going to be worse, right? Test set always perform worse than training set, than your model with training set, because they have not seen your test data set at all, right? Whereas in training set, they have already seen your data, right? So this is unseen data set. As you can see, the performance is 0.249 and RMSE at 78, right? So it's not good. Okay. Once you get the performance, you can also plot the actual versus predicted graph to see how it looks like, the R-square graph. And in order to plot the graph, it's actually very simple as well. Again, you need to define what is your predicted value. So what is your predicted output? So in this case, it's model1.predict X test, right? So predicted output for your test data set. And then here is how you plot the graph. Right, so we use the NumPy polyfit module, and then here again we call our Y test, which is our original actual value of our PM 2.5, and the model predicted value, which is the predicted value of the PM 2.5. Right, so these are some of the graph properties. Pretty straightforward. The figure size, the color, and then we label the graph. So these are pretty straightforward. Scatter here is the type of graph. So it's a scatter graph, scatter plot. So that's why we call the scatter function here. And then also we plot a best fit line to see to see where it lies on our graph. So from here you could see it does not perform as well, right? This is the measured value, and then this is predicted value, and as you can see, it does not perform well. So linear regression is bad, right? It's not a good model for our data set here. So let's take a look at random forest regression model, right? So random forest regression essentially just an ensemble version of a decision tree model, right? So what it does, it generates hundreds of trees, right? Hundreds of decision trees, and at the end of the day, it calculates for the average prediction from all the trees. So in theory, it should give you a better performance, right? And also better efficiency. So what we're going to do here is, again, we already label our random forest regressor as model 2, right? So we just need to call them. So we call model 2, and we perform the fit. We fit that model with our training set, right? So we want to train our model, we fit it with our training set. So X train and Y train. Once we have defined our model and train our model, what we can do now is to check the performance of the training set, right? See how it performed, how good it performed on the training set. So again, the same way, but instead of model 1, now we have model 2, right? Again, just on the training set. And as you can see, the R-square value for our training set now is really good, right? It's a 0.98, right? Around 0.98. So that is really good compared to what we had before, which is 0.249, right? So it has a really good R-square value and also a really good RMSE. Now it's much lower at only 13.6. But again, this is the performance on the training set, a set of data in which the model have seen before, that the model trained on, right? So in order to get a better idea on how our model generalized, on how our model performed with unseen data set, we perform the testing to find the test performance, right? So here, as you can see, we did the same thing, but instead of model 1, model 2, and with our test data set. So this data set has never been seen before by our model. And as you can see, the R-square value is not as good as training set, which is at 0.83 instead of 0.97, but still much, much better than what we have seen with linear regression model, right? And the RMSA value is at 36.9. So not as good, again, not as good as your training set, but much better than the linear regression model, right? So if you get an accuracy above 80%, above 0.8, the model is normally good enough to be deployed. Okay, now, of course, in order to deploy, you will need to test it more with more data set, right? To get a better idea of how good the accuracy or how good your model generalized, right? But as you can see from the test set, we already get a rough idea that it is pretty good. Again, we can plot the graph to see the actual versus predicted graph. And as you can see now, the scatter plot is much better, right? Each sample point is now much closer to the center line, the best fit line, and essentially just a much better performing model compared to what we had before in linear regression. Okay, so that's essentially how you can develop a prediction model with Python code. What I'm going to show you next is a web application that we have managed to build on top of Python that hopefully once it's completed, everyone can access. And the goal here is we want everyone, even those without any programming experience, even those that didn't know how to code in Python, to be able to perform what we have performed just now, right? But easily with just a few taps of a button, right? So just now, when we developed the model, we took about 25 to 30 minutes. So let's see how long it takes us when we just use our web application. So here, it asks us to upload a file. So we choose our file. So we use the same file that we used for our live demo just now. So you can see the file has been successfully loaded, right? So here we can just easily choose the parameter. So we don't have to go through all the codes. You could just tap on the drop-down menu and choose your output parameter. So here I want to predict PM 2.5, and I will display all your input parameters, right? So here I think I set this remove non-numeric. Okay, I set this on, which means that the non-numeric attributes will be automatically removed, but I could also perform label encoding, right? Supposedly I can perform label encoding. So when I check on the parameters, again, NO is just number, right? So we don't want NO, so we just press X and it's gone, right? It's gone. We have dropped that attributes from our data set. And now, let me switch back to PM 2.5 and remove NO. Okay. So now we have all the input parameters as what we have before. But again, we remember that our cumulative wind direction is not a numerical attribute. So let's now convert it to numerical attributes. Again, with label encoding, the numerical attribute has been automatically converted into, I'm sorry, the object variable, the categorical variable has been automatically converted into numerical attributes, right? So we don't have to do anything. Essentially, just by checking this box, we have converted this into numerical attributes. Again, we can see the data statistic here, right? We can see the data statistic. And even if you want to look at, okay, here, you can actually look at the whole data. This is actually the first 100 rows, but you can also display the full data set. Okay, now, missing value is also automatically imputed by the program, so you don't have to do anything. If you have a missing value, the program will automatically impute the missing value, right? If you want to check on the distribution of the graph, you can do that. Just tap on this button, and it will show you the distribution of the graph is now plotting. So take a little bit of time because it's quite a huge data set. All right, so now it's done. And now you can see the distribution of the graph, right? So you don't have to type in any code. Again, just call the function. I mean, just tap on the this checklist, just check the box, and then you can see the distribution of the graph, right? You can plot log graph. You can have a correlation analysis. You can have heat map, right? And then if you want a pair plot graph, you could do that too. So correlation, as you can see now, this is the correlation, right? Again, you don't have to type any code, right? Just check the box. And then you get a heat map correlation right here. And in pair plot graph, you can see the correlation graph between two different variables or even more by just picking that particular variables, and it's supposed to plot the graph. Again, it's a little slow because we have quite a huge data set here at 43,000 rows. But if you compare this to Excel, it's actually much faster. Or other software, it's actually much faster. So you can see here the relationship between PM 2.5 and temperature, right? So it's very convenient. Now we have seen how we can analyze data with this web application, right? But can we predict, build a prediction model? So let's take a look at that now. Okay, so when we tap in on develop prediction model, okay, so as you can see, it immediately developed a linear regression model for me, right? It gave me the test accuracy score, the RMSE score, and training time, 0.06 seconds. So very similar to what we got before, but now we just tap a few buttons. In less than 1 minute, we can get the accuracy of our model. We can build the model, right? You can change the test data size to how many percent that you want. So let's set it back to 20%. Again, you can choose different scaling method, right? It's very easy. You can choose different scaling methods. So let's choose the same one, min-max scalar. And you can perform data reduction, but we're not going to cover that today. It's another topic. But you can perform data reduction on your data set as well just by tapping on it. Okay, let's switch to random forest regressor and see how it performs. So I'm going to take a little bit more time. It's a more complex model compared to linear regression, but you know, a better performing model. Take a little bit more time. Okay, as you can see, 83.27%. So this is test accuracy with the RMSE score of 36.82, right? So we did this, we built this model in 14.5 seconds. So just now, when we developed the model manually in Python, we spent like 25 minutes to a half an hour. But now it just takes you less than a minute, and you can change the tuning parameters easily from here. You can change the tuning parameters, and then it will rebuild the model. So extremely simple, extremely easy to use. we plan to further improve this web application and hopefully make it available to you guys out there. It's still running after we changed the tuning parameter. It's still running. So how fast or how slow it takes to train your model also depends on your computer. So if you have a gaming computer, it will build the model really quickly, right? But if you have just like a normal office computer, it will take more time to develop the model because it requires a lot of computational power. So as you can see, 83.22%, and again, 36.88 RMSE with the new tuning that we did here. So yeah, that's pretty much, I think, for today. We can actually move on to Q&A if there's any questions on our webinar today. And I hope it does give you an idea of how you can develop a model with Python.
Okay, thank you, Danny.
Thank you.
All right. So now,
Thank you.
okay. So now, question and answer session. For those who like to ask the speaker today about the Phyton, how the maybe some of you like to pursue in this model prediction or develop a model or develop your solution in Phyton. Maybe you can ask what are the basic or what is the where to start or relates anything about the Python. Maybe this is the good opportunity for us to ask the speaker. I look from the chat room. So far, the question is about the one asking about the recorded.
Okay.
So and then others yeah, no question for the
Okay.
from the chat room. So maybe we can have live question.
Yeah, maybe you can have a few minutes for questions.
Mm-hmm.
Or you can use the chat room as well.
Yeah.
Okay, how does Python replace the missing data? Is it just by inserting random value? No. So what we did was we did median value substitution. So essentially, for that particular parameters, it will find what is the median value, and it will just replace the missing value with the median value of that particular parameters. So it doesn't just insert random values, right? So median value, you can roughly get a really close value, like to represent your whole data in that particular parameter. So it should be quite good to replace your missing value instead of just inserting random value. The next question is, can we use Jupyter Notebook to build model? Okay, so Jupyter Notebook is actually sort of like I would say a web application in a way that allow you to run each code line by line, right? So if you use IDE like PyCharm or Anaconda, or if you just use terminal, you normally have to write the whole code and then run the whole thing at the same time and see what's going on. So you couldn't just run like line by line, but with Jupyter Notebook, you can actually run line by line, which I think is a much better option for data analysts or if you want to build machine learning model, because you can see everything that's going on, right? So Jupyter Notebook is sort of another version of your IDE. So yes, you can definitely build a model with that. Any more questions? Can Python perform hybrid modeling, first principle with data-driven model? You can, but if you want to build sort of like a hybrid model, maybe you want to introduce your own equation to the model, then you have to access the source code of that particular library that you use and change some of the equation in that particular model. You cannot just use the default model. It will get more complicated, but yeah, it's possible. Can we integrate the Python model in MATLAB or PySys? Okay, I have personally never tried this before. Maybe Fauzi have some insight on this. I've never personally tried this before, but I don't know if it's possible.
All right. For the Phyton MATLAB, yes, it's possible to integrate. Let's say you build the Phyton, but
Okay.
you need to convert to the DLL or any COM object. Then you can call in MATLAB, or in HiSys there's a block, custom block. Maybe Dr. Riza can add up on that
Thank you.
for HiSys application. All right, Danny, if
Okay.
you can share, my question is, when you run the system, so what is the minimum requirement for a PC to run Phyton?
Okay, good questions. I think Python is quite an efficient language, which means that even if you don't have the most powerful computer, you can still run it. So let's say today, what is the standard basic laptop like i3 CPU with maybe 4 to 8 gig of RAM? It should be enough to run Python. But maybe you cannot perform a complex analysis. For a simple analysis, you can definitely use that basic laptop. But if you want to perform a more complex analysis, you can actually use Google Colab. Google Colab is completely free. You can use their web application to build your Python model, to build a prediction model and store it in Google Drive, right? So those are completely free, and you can utilize the cloud CPU and GPU from Google. So it's very powerful. You can do video processing, you can do object tracking with it. So, and it's completely free. So if you don't have a powerful computer, don't worry. You can use Google Colab to build your model. That's what I do. If it takes too much computational power, I'll use Google Colab.
Okay, thank you.
Thank you.
And any question before we leave, before we adjourn the session? Any additional question? Maybe we can take one or two.
Yeah,
Right.
sure.
Okay, I have a few announcements. We will have a group session, a photo session. Okay, that's one. Another one, announcement. We will have a series of webinar from MyPCS, Malaysia Process Control Society. So it will be March, April, May, and June. So we invite a few prominent speakers from Process Control Society. To name is from Professor Thomas Marlin, Prof. Sigurd Gestet, Prof. Namabukano, Prof. Jibao. Those are very prominent researcher or professor in this process control society. So I hope we can see you all again or join this session. And for Phyton series, we will have a session next month, 17 March. The poster or the invitation will be emailed soon. So it's about introduction of Phyton to MATLAB user. So it's a bit it's on more on workshop platform. It's cover 2 to 5 on the 17 March. Yeah, the speaker will be from University Kebangsaan Malaysia, Mr. Muhammad Nazri.